be talking about properties of solutions, molecular forces, colligative properties, vapor pressure, surface tension, viscosity, osmosis, and some clinical applications. Physical properties can be divided into two categories. There are extensive properties and intensive properties. Extensive properties are things like mass and volume, which depend on the size of the sample. And intensive properties are things like density and concentration, which are characteristic properties of a substance, but they don't really depend on the size. So you can have any size sample that's being studied, and that doesn't affect the intensive properties. There's a third category that we're going to introduce today, and that's colligative properties. Colligative properties can only be applied to solutions, and a colligative property depends only on the ratio of the number of particles of solute or solvent in the solution, not the identity of the solute. So there are four recognized or four-sided colligative properties that we look at a lot, and those are vapor pressure, boiling point, freezing point depression, and osmotic pressure. And all these properties assume that the solutions are ideal solutions. So we're going to be looking at those today. And their behaviors. Well, for example, a lot of our medications and things that we give to our patients, we give in solution. So we need to understand how those solutions work and how things interact. A good example for us is if you think about lidocaine. We give lidocaine to our patients in like 1% or 2%, a pretty dilute solution. And it stings initially when we inject that under their skin. So imagine what the pain would be if you did, pure lidocaine hydrochloride under the skin of a patient. Also, some of our medications come as solids, and it's up to us to dissolve them into some sort of a solvent in order to deliver them to our patients and know what the concentration is that we're given. So we need to understand some basic terminology, and we need to understand how solutions work. So a solution is a homogeneous mixture that contains one or more solutes that are uniformly dispersed at the molecular or the ionic level throughout the solvent. And by homogeneous, that just means that the mixture, it's not possible to discern the phase boundaries between the components of the mixture. So the phase boundary would be what separates the regions of a mixture, where you would be able to see a difference in their chemical or their physical properties. And with a homogeneous mixture, you can't see that. So the best example would be normal saline. If you think about normal saline, it's just 0.89% sodium or sodium chloride, and it's 99.11% water. But if you look at normal saline under a microscope, you can't see where the ions in the normal saline are or where the pure water is. So it's a homogeneous solution, or it's uniform throughout the sample. So the solute in the material gets dissolved, and the solvent is the material that does the dissolving. Although these are probably, fairly casual definitions, that's what they are. Solutions, though, are not necessarily liquids. Other things can be solutions. For instance, the air that we breathe is a solution of nitrogen and oxygen and a whole bunch of other little minor gases that I can't think of the names of right now. We also have mixtures when we do anesthesia of oxygen and nitrous oxide. That's a solution. The fillings that they put in at the dentist office are usually made out of some sort of solution of like silver and mercury, or silver and some other type of metal. So that's a solution. If we look at the fundamental differences in the state of matter in the different particles, we can see that the solutions can be gases, they can be liquids, or they can be solids. And a lot of it has to do with the state of the particles and how close together that they are. And again, the different phases. Can you see a phase difference? Can you see a separation difference? So the state of a substance is at a particular temperature and pressure, and that is going to also think about the kind of bonds that hold solutions together, or the kind of forces. So, the attraction between molecules, which is intermolecular attractions, are not nearly as strong as the attraction that hold compounds together, or the intramolecular attractions. But with intermolecular attractions, they are strong enough to control some of the physical properties that we're interested in, things like the boiling and melting points, the vapor pressure, and the viscosity. So these intermolecular forces are collectively grouped together as van der Waals forces. I think that's a term we've talked about in the past, as van der Waals forces. And van der Waals forces just is a general term that's used to define the attraction of the intermolecular forces between molecules. So one of the properties of liquids that's important is viscosity. We think about viscosity a lot when we think about plasma and about blood. Resistance of a liquid to flow is called viscosity, and it's related to the ease with which molecules can move past each other. So a liquid flows by sliding molecules over one another. Viscosity increases with stronger intermolecular forces and decreases with high temperature. Another place other than our body that we think about viscosity is our cars. The Society for Automotive Engineering rates motor oils based on viscosity. So motor oils use a rating system to class. Absolute viscosity is expressed in terms of the actual force required to overcome internal friction. The unit of absolute viscosity is called the poise, named after Poiseuille. It can't be mathematically calculated, it has to be measured. 1 poise is a force of 1 dyne per second per centimeter squared. The dyne is the quantity of force which accelerates a mass of 1 gram 1 centimeter per second. Relative viscosity is a comparison of the viscosity of one fluid with that of another fluid under identical circumstances. So, ordinary viscosity is expressed in terms of relative viscosity. That is, the viscosity of the liquid is compared to that of water at 20 degrees Celsius. So the viscosity of water at the temperature is designated as 1. In the comparison of gases, air is used as the reference. So viscosity is the measure of substances' resistance to motion under an applied force, and viscosity is affected by temperature and pressure, and in cases of solutions, it can be affected by composition. And we compare that, you can again have absolute viscosity or relative viscosity. And with relative viscosity, we compare that to either the composition of water or the composition of air. Viscosity, it's important to remember that when the book speaks of these things, they're talking about ideal fluids and ideal gases, and those are things where there's no loss of energy due to. So as we talk about viscosity and flow, some of the things that we think about are our gases: oxygen, helium, nitrous. Of course, we use olive oil a lot because that's supposed to be comparable to some of the fluids in the body, and then benzene. So the molecules will interact with each other and with the tube or the pipe as the fluid flows or as the gas flows. So the movement of the molecules next to the pipe is going to be practically zero because you're going to have friction and you're going to have things that slow it down there. But near the center, they're going to be moving a lot faster. So as fluid approaches an orifice, the pressure is going to increase slightly, and then it's going to drop suddenly as the orifice is passed. So as it comes out the other side of the orifice, the pressure is suddenly going to drop. So the coefficient of viscosity is just going to be a measurement for that. So through a tube, for instance, benzene's flow is going to be 130 times greater than olive oil, but through an orifice, the flow will remain the same. So you have to remember, if you have a tube, it's going to slow things down. So think about like giving IV fluids. And if you're going to try to give a lot of IV fluid very quickly, then you're going to want a short, fat IV catheter, versus if you maybe putting something in because you want it to stay there a lot longer. You may put in something that's much longer and much thinner. But if you need to give a lot of fluid really fast, you're going to try to use something that's short and fat. And this helps to explain that flow. Surface tension comes to mind. Surface tension results from the net inward force experienced by molecules on the surface of the liquid. The bulk molecules, which are those that are in the liquid, are equally attracted to all their neighbors, but surface molecules are only attracted inwards towards the bulk molecules. They're not attracted to things that are above them or anything like that. So the surface molecules are packed more closely than the bulk molecules, and that causes that liquid to behave almost as if it has a skin. So molecules in the liquid state are attracted to all of their neighboring molecules by these intermolecular forces, but the molecules near the surface experience these attractive forces to all of the surface molecules and just the molecules below it. So there's not really a balancing or anything for those attractive forces above the surface. So those stronger intermolecular forces cause a higher surface tension. Water has a high surface tension because of the hydrogen bonding. So this is important when we think about like surfactant for our neonates and their lungs, and to decrease the work of breathing, you have to decrease that surface tension, or you have to break that surface tension or that skin. So the surface tension of a liquid varies with the temperature and the purity of a liquid. The surface tension of water decreases as the temperature increases. Certain chemicals, particularly substances possessing long carbon chains, will lower surface tension. So in other words, they're going to decrease the attraction between the interior and the outer molecules of those fluids. Surfactants are going to lower surface tension. They're going to improve a solvent's ability to be a solvent by reducing the surface tension of the solvent. So examples of surfactants are things like what we spray on our clothes for like greasy stains, and then also the surfactant that we use to help babies to be able to breathe better. Surface tension is the tendency of a liquid to shrink into the minimum surface space possible, and surface tension is like what physical property is necessary, for instance, to let insects kind of float and slide across the surface of water, because it has that skin or that surface tension on it. If you think about the application of surface tension in clinical medicine, surface tension is a phenomenon that occurs at an interface of two dissimilar immiscible substances, so that the surface tension is linked with and related to absorption. A substance which reduces the surface tension of another substance accumulates on the surface layer of that substance and then is readily absorbed. So for us, the best example is probably the surfactant that we give the neonates so that they can breathe better. So a guy named Traub studied the idea of surface tension, and he came up with a rule that helps us some. Traub's rule is a relationship between hydrocarbon chain length and surfactant activity, and it basically states that for every extra hydrocarbon group in a surfactant molecule, that the surface activity approximately triples. So shorter chain length molecules have less surfactant activity than higher chain length molecules as far as emulsification and and breaking that surface tension. So that means you can get away with using a much lower concentration of a longer chain length surfactant. It's interesting to note that they use travel. The vapor pressure of a liquid results from the most energetic molecules near the surface of the liquid escaping into the gas phase. The most likely escape sites for the liquid molecules are at or near the surface of the liquid. At any temperature, some molecules in the liquid are going to have enough energy to escape the bulk liquid, and these molecules are going to move into the gas phase. As the number of molecules in the gas phase increase, some of the gas molecules are going to strike the surface and return to the liquid. As more molecules escape the liquid, the pressure they exert increases. After some time, the pressure of the gas will be constant. Substances that have greater intermolecular forces have lower vapor pressures. The most energetic molecules in the liquid are going to have sufficient kinetic energy to overcome the intermolecular forces so that they can escape that liquid phase and enter the gas phase. As temperature increases, the vapor pressure of the liquid increases, and so does the volatility. Volatility is a non-quantitative term that describes the tendency of a liquid to evaporate. More volatile liquids evaporate more readily than less volatile liquids. So the liquid and the vapor reach a state of dynamic equilibrium, and liquid molecules evaporate and vapor molecules condense at the same rate. So dynamic equilibrium is a condition where you have two opposing processes that are occurring simultaneously at equal rates. A liquid boils at a temperature at which its vapor pressure is equal to the pressure of the gas above it. The lower the pressure of a gas above a liquid, the lower the temperature where the liquid is going to boil. As the liquid is heated, its vapor pressure increases until the vapor pressure equals the pressure of the gas above it. Bubbles of vaporized liquid contain gas inside the bubbles. So that form within that bulk liquid, and then they rise to the surface where they're going to burst open and release the gas. At the boiling temperature, the vapor inside of the bubble has enough pressure to keep the bubble from collapsing. In order to form vapor, the molecules of the liquid must overcome the forces that attract them to be together. The temperature of a boiling liquid remains constant even when more heat is added. The boiling point of a liquid is the temperature at which its vapor pressure is equal to the pressure of the gas above it. So normal boiling point of a liquid is the temperature at which the vapor pressure is equal to 1 atmosphere or 760 torr. And if you look at the diagram, it shows you some common, water, ethyl alcohol, diethyl ether, which is the ether that we use in anesthesia. It shows you these liquids, and it shows you what their boiling point is, what their vapor pressure is. So, and that's why we make you all memorize the vapor pressures of the various anesthetic gases that we use now, the desflurane and the sevoflurane and the isoflurane, because you need to know at what pressure and at what temperature that those are going to boil at. So the temperature of the boiling point increases as the external pressure increases. So you can get two different ways to get a liquid to boil, and that's to either increase the temperature or to decrease the pressure. That's how pressure cookers work. As you increase the pressure, you have to have less temperature. Food that's cooked at higher elevations, like if you hike up really high in the mountain, you have to cook your food longer, or you have to cook it at a higher temperature because you have less pressure high up in the mountains. So you have to cook it for longer, or you have to somehow add some pressure to it. So we've already said that solutions are homogeneous mixtures of two or more pure substances, and in solution that you need a solute and a solvent. Here's some examples of different solutions and the state of the solvent and the state of the solute. The intermolecular forces between the solute and the solvent particles must be strong enough to compete with those between solute particles and the solvent particles. The solvent pulls solute particles apart and surrounds or solvates them. And an ionic salt is soluble in water. It's because the ion-dipole interactions are strong enough to overcome the lattice energy of the salt crystal. So the solvent just surrounds those particles until they are dissolved. So a good example of an ion-dipole interaction is sodium chloride in water again. The sodium ion is attracted to the oxygen end of that water molecule because it has a negative dipole, while the chloride ion is attracted to the hydrogen end of the water molecule because it has the positive dipole. A solution is a solution in which the solvent is not capable of dissolving any more solute at a given temperature. The physical properties that can be divided into two categories: extensive properties, which are things like mass and volume, which are to depend on the size of the sample, and the intensive properties, such as density and concentration, which are going to be characteristic properties of the substance, but they don't necessarily depend on the size of the sample. So this area, this section, is going to introduce a third category, and that's a subset of those intensive properties of a system. And that third category is the colligative properties, and they can only be applied to solutions. So by definition, one of the properties of a solution is a colligative property if it depends on the ratio of the number of particles of solute and solvent in the solution, not the identity of the solute. Discussed, the vapor pressure of a liquid results from the most energetic molecules that are near the surface of the liquid escaping into the gas phase. The most likely escape sites for the liquid molecules are at or near the surface of the liquid. So as we begin to introduce solute molecules, some of these escape sites are occupied by those solute molecules. That means there are fewer solvent molecules that can escape into the gas phase. Therefore, the vapor pressure of the solution is less than the vapor pressure of the pure solvent. That's kind of like why we add salt to water, so that it'll make it boil faster. Raoult's law gives the quantitative relationship between vapor pressure and solute concentration. Raoult's law states that vapor pressure of a volatile component of a solution is equal to the vapor pressure of the pure substance times the mole fraction of that substance. So we can calculate vapor pressure by using Raoult's law. Raoult's law assumes that there is an ideal behavior based on the simple microscopic assumption that the intermolecular forces between unlike molecules are equal to those between similar molecules. So that would be conditions for an ideal solution or an ideal gas. Exercise to show you how you can use Raoult's law to calculate the lowering of vapor pressure. So if we read the problem, it says that glycerin is a non-volatile, non-electrolyte with a density of 1.26 grams per milliliter at 25 degrees Celsius. And you want to calculate the vapor pressure at 25 degrees Celsius of a solution that's made by adding 50 mils of glycerin to 500 mils of water. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr, and we have that from Appendix A. So the first thing that you're going to need to do is be able to calculate the molar mass. If you remember how to molar mass, that's just in chemistry, to calculate the molar mass, that's just a property that's defined as the mass of a given substance. So you have to go back to your periodic table of elements, look at your individual elements, and add that together to get your molar mass. So if we do that for the glycerin, we're going to find that the molar mass adds up to 92.1. And if you look at the molar mass of water, that's going to be 18. So now we need to look at our individual items here separately and calculate the moles. So for a mole of glycerin, and we know that we're going to be given 50 mils of glycerin. So the 1.26 grams of glycerin, that's the density from our problem, per mil is our first part. And then we know that 1 mole is 92.1 because we calculated that from the molar mass. So if you divide the 1.26 grams by the 92.1, that's going to give you some very tiny number that I haven't calculated. And then multiply that by 50. That should come out to 0.684 moles. Then go back and do the same thing for the water. You know, we have 500 mils of water, because we get that from the problem, and 1 gram of water over 1 mil of water, and then times the 1 mole of water over the 18 grams, because that's the molar mass of water. So again, if you divide 1 by the number 18, or put 18 into 1, and multiply that by 500, you should get 27.8 moles for the water. So then we can use Rayout's law to calculate the vapor pressure, because we know that the pressure of the water is going to equal the vapor pressure. So if you do your 0.976 times your 23.8 torr, that's going to give you 23.2 torr, and that is going to be lower than the vapor pressure that we started off with, which was, let me go back to the problem, 23.8. Yes, so 23.2 is 0.6 lower than 23.8.